Okay, so please listen. Okay, what we're going to look at today is using probability to make decisions and make predictions. Now, a big part of probability is oftentimes, some of you are talking and should be listening, thank you. Oftentimes, we actually use those probabilities to help us make a prediction of what might happen in the future, okay? So, if we look at the first scenario, it says, I don't know if I can get it to flip screens here. Okay, Kate sells shirts and caps that have a school logo on them. Both the shirts and the caps are available in purple or gold. The table shows the number of shirts and caps that Kate sold during her first week of business. Okay, so she's starting a business, she's selling shirts and caps. She sold 125 purple shirts, 75 gold shirts, 60 purple caps, 40 gold caps. Okay, we're going to just go through and answer these questions, and it'll all kind of fall into place. So what was the total number of shirts sold during the first week? Total number of shirts sold would be what, Ellie? 200, right? You'd add the purple and the gold together, sold 200 shirts. So far, so good. That's an easy question. Okay, the next one. What fraction of the shirts that were sold were purple? Abby? 5/8, right? You'd put 125 out of the 200 were purple, which really simplifies down to 5 out of every 8 shirts that were sold were purple. So far, so good. Okay. Now, Kate assumes that future sales will be similar to the first week's sales. So she's assuming that going forward, she's going to continue to kind of sell stuff at the same rate. Okay? She plans to order 2,000 more shirts. How many of these should be purple? Because you don't want to just place your order and say, I want to get 2,000 purple shirts. Because if you do that, you're probably going to run out of gold shirts and then not be able to make any more gold shirts. And if you're selling them at the same rate, you kind of want to figure out how many of each. Okay, this is where we have to go back to proportions, right? This is really a probability, 5 out of every 8. Okay, that's our probability of getting a purple shirt. When we do this, we're going back to proportions. We're using that fraction, 5 out of 8. This is 5 purple out of 8 total. The question is, how many do we want to be purple out of what? 2,000. So we put 2,000 on the bottom, and then we just solve this. So how many of the shirts should she order and have them be purple? Oh, 1,250 should be purple. Is she guaranteed to sell 1,250 purple shirts? Probably not, right? Because this number here is experimental probability, right? That's what actually happened. Is what actually happens the same as what should happen? Not always, okay? But we can assume that it's probably going to be close. Okay, in general, when Kate sells a shirt, what is the probability she sells a purple shirt? 5/8, right? The probability of purple is 5/8 or 62.5% if we change it to a percent. Okay, so then let's look at caps. What's the total number of caps sold during the first week? Lola? 100. What fraction of those sold were gold? Reckon. 2/5, right? 40 out of 100, which simplifies to 2/5. Kate places an order for 5,000 more caps. How many should be gold caps? We're going to use that fraction, 2/5. 2 out of every 5 were gold. Where should I put the 5,000? On the bottom. And we solve this. What do you get, Sydney? 2,000 gold. The rest she should order purple. Questions there? Is that kind of making sense? Pretty simple. I'd say that's probably easier than the last couple days.
Yeah.
It's easier to wrap your head around because we've already done proportions. That's nothing new to us. Okay? So, flip the page. All right, at a carnival, a spinner is used to determine a player's prize. If the spinner lands on red, the player gets a stuffed animal. Suppose the spinner is spun 160 times. What is the best prediction of the number of stuffed animals that will be given away? Okay, so if you just spun the spinner once, what fraction of the time, or a few times, what fraction of the time, what's the probability of landing on red? 1/8. 1 out of the 8 are red. Okay. How many times did they spin the spinner? 160. So we're going to put 160 on the bottom. X on the top. And we solve this. What do you get? Ellie? So you would expect to win a prize 20 times. You should, right? Okay, now we're going to just hang tight for a minute. After lunch, we're going to actually conduct a simulation. Okay, what does simulation mean? Okay, what does that mean though?
It's like where you run the experiment so that what should happen.
Right, so we're going to conduct a simulation to see if what should happen matches what actually happens, right? Because right now this is what should happen. We don't know if that's what's actually going to happen, okay?
This is at a carnival because they probably waited it on that.
Oh, you think so? Because at a carnival they always cheat, right? It's always rigged.
Always. Yeah,
Always.
like the rims are like tight.
Yeah, that is true. Like when you shoot basketballs at a carnival, they're either like the hoops are not oval, they're not circle, they're oval.
The basketball like exact.
Yeah. So yeah, they do cheat a little bit. Well, we're gonna assume that there's no trick here. They're not cheating. Okay. Okay. So let's go to lunch. We'll do that after lunch. Okay. So what we're gonna do is I don't have spinners. Okay. So what we're gonna do instead is we're gonna flip a coin. Now, in order to simulate this, we need to have something happen in theory, 1 out of every 8 times. Okay? The way to do that is to flip a coin 3 times and record what happens. Okay? So when you flip a coin, you can get heads or tails, right? So your options when you flip it 3 times is you could get heads, 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 tails, 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 heads, tails, heads, 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 tails, tails, heads, tails, 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 heads. I'm missing heads, tails, tails, and tails, heads, heads.
Wait, you already have.
So there's 8 possible outcomes.
One heads, tails.
No, because you're looking at your first flip, second flip, third flip. Okay? So I'm going to give you each a coin. Okay? And each of you are going to go through this, and you're going to flip the coin 3 times and do it a total of 6 times. So really you're flipping the coin 18 times, right? Does that make sense? You need to keep track of what you get, okay? So if I'm flipping the coin, I'm keeping track of, okay, I got tails, and then tails and tails. So I'm going to keep track. My first round, I got tails, tails, tails. Then you're going to keep track. Shh, ladies and gentlemen. Then you're going to do that again and keep track of what you get. You're going to do that 6 times. Keeping track of what you get each time. Okay, make sense? Okay, each one of you is doing this because we need 160 trials. Okay?
So how many times do we have to do it?
Where do we keep it?
On your paper.
Anywhere.
Anywhere on your paper.
That's my.
Those are heads. Yeah, you know, like.
Brother, can you grab that?
Okay. So you're doing this 6 times, 3 flips for each one. Nope.
Go.
I hold it between my thumb and my finger, like this, not sitting on top of it.
Except a little less.
It doesn't matter, just throw it up and catch it. It doesn't matter.
Daddy, let me see you put this.
Two times. I got heads, tails, twice and tails, heads.
I got head, tails. I get it.
I got that twice and tails.
Wait, we both only do this one time, right?
No, each of you has to do a total of 6.
1, 3.
3 times.
Oh my god. Let me do it.
Hang on. Okay, once you have your 6 results, you're just doing 6. Once you have your 6 results, bring your penny up here and put it in my jar. I'm poor. I need every penny I can handle. I'm a teacher. That's why. That's why my mom quit. I'm totally kidding.
What she telling me? She's like, Lola, if you want to get a good job, don't be a teacher.
Okay, so
You're actually
hopefully you're almost done.
I'll just like
Okay, so you guys, a simulation, right, helps us see what could actually happen. Now, I had you guys all do this 6 times, and I did it 6 times. That would only be 100, there's 25 of you plus me, that's 26, times 6 is 156. So I did it 4 more times, so we'd have 160 trials, okay? Now, if I want the probability to be 1/8, I'm gonna go with heads, 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 okay? How many times did heads, heads, heads occur? I got heads, heads, heads 1, 2 times. Okay? How many times did you get heads, heads, heads?
Once.
So 1,
0. Wait, actually.
heads,
Yeah,
heads,
0.
0. Tyler?
0. 0.
0.
0.
Up here? How many times did you get heads, heads, heads?
0.
1.
0.
1.
0. 0.
2.
2. Okay.
Oh, good job. 0. 1.
0.
1.
0.
So we got heads, heads, heads. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 out of 160. So if that happened, 12 out of 160 tries, what should have we gotten? 20. That was our prediction. Our prediction was that we would get red 20 times. We didn't. We only got it 12 out of the 160 trials. Okay, we weren't super far off. Now, if we did this another 160 tries, would we maybe get closer? Yeah. Okay, because the more you run a simulation, the closer you should get to the actual probability of that happening. Okay, the more you do it. If you only flip a coin once, well, that's not really a good test. If you do it 500 times, that's a much better test, okay? 160 is a pretty good amount of times to try something, and we were partially there, okay? Just not all the way. Questions there? Does that make sense? Okay, so we understand what a simulation is. We understand how probability affects that, okay? We learn how to flip a coin. Okay, last slide. Deciding whether a game is fair. Okay, I hear this all the time. That's not fair. That's not fair. He was cheating. That wasn't fair. Okay, I know. Okay, so in order for a game to be fair, okay, if I'm gonna play a game with you guys and I say we're gonna flip a coin, if you get heads, I win. If you get tails, you lose.
Well, you win either way.
I win either way, right? Okay, that's not fair. I said if I get heads, I win. If I get tails, you lose. Okay, that's a good way to trick your little sibling.
I was gonna say, I was
It's
gonna
a good way to
say.
trick.
I'm doing that.
Okay, so okay, 7th graders, everybody listen. 7th graders. Some of us are not doing a good job of listening. Okay, so in this game, 2 players each roll 2 fair dice and add the 2 numbers. Player A wins with a sum of 6 or less. Otherwise, player B wins. We're trying to decide if the game is fair. So first of all, what we need to know is what are all the possible outcomes. Okay, when you roll 2 cubes. Now I know this is in your packet at one place. We're going to write them down. You could get a 1 and a 1. You could get a 1 and a 2, a 1 and a 3, 1 and 4, 1 and 5, or a 1 and a 6. Okay? You could write these down. This is going to help you.
I'm going to do 1 and 6 because that would be 7.
You're right, Mason. You're rolling 2 cubes. You could roll a 1 on the first one and a 6 on the second one. Right? Okay. Then you could roll a 2 and a 1, a 2 and a 2, a 2 and a 3, a 2 and a 4, 2 and a 5, a 2 and a 6. So far, so good. We could roll a 3 and a 1, 3, 2, 3, 3, 3, 4, 3, 5, and 3, 6. You're seeing the pattern? Then you could roll a 4 and a 1, 4, 2, 4, 3, 4, 4, 4, 5, 4, 6, 5, 1, 5, 2, 5, 3, 5, 4, 5, 5, 5, 6, and finally 6, 1, 6, 2, 6, 3, 6, 4, 6, 5, and 6, 6. Okay, take a moment, finish writing those all down. So you have all the possible outcomes of rolling 2 number cubes. Which means there are how many possible outcomes? 36, right? Okay, now player A wins with a sum of 6 or less. So if you add the 2 cubes together, if it's 6 or less, player A wins. So that means this one, player A would win. 1 plus 1 is 2. 1 plus 2 is 3. Would player A win on 1 plus 6? No. Okay, player A would win here. They wouldn't win there. 2 plus 5 is 7. Player A would win there. Player A wins just on those 2. Player A wins there. Doesn't win anything there. So the probability of player A winning 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 out of 36 tries. We can divide that, we can simplify, divide by 3, 5 out of 12. It says player B wins all the rest of the time. So if player A won 15 out of 36 times, 36 minus 15, player B wins 21 out of 36 times, which is 7/12. Is this a fair game? No, it's not fair because player B has a better chance of winning. There are 6 more times that player B could win. Now, if I said, I want you to change the rules of the game to make it a fair game, because we know somebody will end up crying if it's not fair. Always happens, does every time somebody cries.
Yeah.
So it's got to be fair. If you had to change the rules of the game, how could you make the game fair? You're still rolling 2 cubes. You're still going to add the numbers together. Reckon.
7 or more?
If you get 7 or more, but isn't that what B gets?
7 or less.
So you're saying A wins if you get 7 or less? Well, now that means that A gets all of these. So now A is up to 21 out of 36 and B is at 15 out of 36. So still not fair. In order to be fair, each person has to have 18 out of 36, right? Each person has to get half. So how could we make it fair, Eddie?
Even and odd.
Evens and odds. If you roll an even sum, A wins. If you roll odd, B wins. Then it would be a fair game. Does that make sense? Questions there? Okay, put that away.